So good morning dear students. Today we will start with the second part of the first chapter, that is Coulomb's law. So in the beginning of the chapter, that is an introduction part, you have already seen different types of charges, that is positive and negative charges, important properties of charges, and different types of charging methods also. So these are some important introduction of that chapter 1. Now most important topic of this chapter is Coulomb's law. The contents of this presentation is mainly Coulomb's law, its mathematical expression and vector form of Coulomb's law. Charles Augustin de Coulomb, he was a French physicist. He gave an important theorem which gives the force of interaction between charges. Basically, we are dealing with charges. This theorem gives what are the factors in which the force of interaction between these two charges depends. So let us understand what is Coulomb's law in detail. So before going into the detail of Coulomb's law, we need to understand an important term we are using in this chapter, throughout this chapter, that is point charges. So by definition, when the linear size of charged bodies, in each charged body, if their size is much smaller than the distance that's separating them, then we can neglect the size, right? The size can be ignored and we can call it as point charges. So this is what a point charge is. So you should understand what is the meaning of point charges. It is a very small, negligible sized charges. Now we will understand what is Coulomb's law. So if you have two charges, 2 point charges, according to Coulomb's law, the force of interaction, the force between these 2 point charges is directly proportional to the product of the magnitude of 2 charges and inversely proportional to square of the distance between them. And this force acted along the line joining the 2 charges. That is, if you have 2 point charges Q1 and Q2 separated by a distance r in vacuum, the magnitude of the force between them is given by F is equal to K into Q1 Q2 by R square. This modulus sign is put to understand the product of their magnitude, of these 2 charges, divided by R square. R is the distance between. So we'll understand it in detail. The electrostatic force of interaction. What do you mean by force of interaction? If you have 2 charges, there will be a force of interaction. It can be either attractive or repulsive, depends on the nature of the charges. Suppose both the charges are positive, or both the charges are negative, we can say they are repulsive. If they are opposite charges, the interaction will be attractive. So that is the meaning of force of interaction. This force of interaction between 2 point charges is directly proportional to product of their charges. If you have 2 charges, the product of their magnitudes, and inversely proportional to the square of the distance. If they are separated by some distance r, then inversely proportional to square of the distance between them. And they should act along the line joining 2 charges. And it is actually applicable to what type of charges? Stationary point charges. Stationary point charges. So let us see it mathematically. For that we are considering 2 charges Q1 and Q2 separated by a distance r. Then by the first statement, F is directly proportional to product of their charges Q1 and Q2. So F is proportional to Q1 into Q2. And inversely proportional to square of the distance. Since it is inversely proportional to the square of the distance, we write F is proportional to 1 divided by R square. So these are the two statements. F is proportional to Q1 into Q2. F is proportional to 1 divided by R square. So combining these two, we can write F is proportional to Q1 Q2 by R square. Clear? F is proportional to Q1 Q2 by R square. Now in any mathematical equations, if you are removing this is proportionality sign, proportional. So this proportionality sign, if you are converting it to equality sign, we have to introduce a constant. So F is equal to a constant K. The small letter K is used here, okay? Small letter K into Q1 Q2 by R square, where this K is the proportionality constant or electrostatic force constant. So value of K is given by, small letter K is given by K is equal to 1 divided by 4 pi epsilon 0. So this is another simple introducing, we are introducing a new simple epsilon. It is a Greek letter epsilon, and 1 0 is also introduced to understand this we are considering in free space or in vacuum. So we'll understand what is epsilon in detail. So in order to understand epsilon, we have to introduce a term absolute permittivity of the medium. Absolute permittivity of the medium. So epsilon is called absolute permittivity. It is actually the property of the medium. Based on the what medium we are keeping the point charges, the force of interaction also changes. If you are keeping the point charges in vacuum, there will be a force of interaction. If you are introducing a medium in between them, then force of interaction changes. So based on that, we define a term, a constant term called permittivity. Permittivity, how much electric field, how much electric force is permitted in the particular medium. So the property of the medium which changes the force of interaction between 2 point charges is called permittivity of the medium. Absolute permittivity is denoted by Greek letter epsilon. This is a simple used, and it is given by epsilon is equal to epsilon 0 into epsilon r. So this is the formula for epsilon. So this is the absolute value of permittivity. So it depends on epsilon 0 and epsilon r. So what is epsilon 0? It is the permittivity of free space. Epsilon naught is the permittivity in free space, and this epsilon r is the relative permittivity of the medium. So epsilon r and epsilon naught, okay, do not confuse. So epsilon naught is the permittivity in free space, epsilon r is the permittivity or relative permittivity, that is the permittivity of the particular medium, relative permittivity of the medium. Another name for epsilon r is dielectric constant, denoted by letter capital K. Capital letter K is also used instead of epsilon r. And one more important point here you need to understand is presence of any medium between these two charges reduces the force of interaction. So we'll prove it in the next slide. The introduction of medium reduces the force between charges. The value of this epsilon r, dielectric constant, is for any particular medium is always greater than 1. Okay, for vacuum it will be 1, but for any medium it will be greater than 1. Epsilon r is given by, based from this formula. From this formula, epsilon is equal to epsilon naught into epsilon r. So we can write epsilon r is equal to epsilon divided by epsilon naught. So keep remember this formula, okay? This formula is important, and this term is also very important. Now see once again, the proportionality constant small letter k. Small k and capital K you should not confuse. What is small letter k? The proportionality constant given by 1 by 4 pi epsilon naught for vacuum and 1 by 4 pi epsilon for medium. And capital K is that epsilon r, that is the dielectric constant. This is capital K. So once again I'll repeat, small k is given by 1 by 4 pi epsilon for medium, any medium, where epsilon is the absolute permittivity. Then capital K or epsilon R is the relative permittivity, which is given by epsilon divided by epsilon naught. So we can write the equation of Coulomb's law for vacuum as well as for medium like this. For vacuum and medium, what will be the difference? Only difference comes in this term. For vacuum we have only epsilon naught here, and for medium you have epsilon naught and epsilon R, that means epsilon here. So F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square in vacuum, and in medium F is equal to 1 by 4 pi epsilon naught into epsilon R Q1 Q2 by R square. Why this difference comes? Because we have seen in vacuum the value of epsilon R will be 1. So we have only epsilon naught here. Then this value of epsilon naught is found experimentally, and it is given by epsilon naught is equal to 8.854 into 10 raised to minus 12 Coulomb square per Newton per meter square. This unit you will get from this equation. And try to remember this value. Same way this equation, usually we are using the equation of Coulomb's law in vacuum, solving numericals and all. This equation is used. Condition of vacuum is used. So F is equal to 1 by 4 pi epsilon naught. This term is again a constant, k, small letter k. This is a constant term. We can find out the value by substituting the value of epsilon naught pi, and this value is obtained as, this is the exact value, but we can use this approximated value, this value. 9 into 10 raised to 9. Just remember this value, 9 into 10 raised to 9 for 1 by 4 pi epsilon naught. Unit Newton meter square per Coulomb square. So try to remember this value, okay? There is a question related to this, whatever we have discussed now. The question is, if any medium is introduced between 2 point charges, by what factor does the force in air or in vacuum, F air or F naught, the notation is F air or F naught, changes? And I have mentioned a point, if a medium is introduced between the charges, actually the force of interaction reduces, okay, reduces. So initially if the force of interaction between two charges when they are kept in medium be F air, denoted by F air, then we'll find out if the medium is introduced, what is the force of interaction. We'll write down the mathematical formula, we'll get a relation, very simple one. So this is the first equation, force in air, or Coulomb's, by Coulomb's law we have 1 by 4 pi epsilon naught Q1 Q2 by R square. Second equation, F in medium, 1 by 4 pi epsilon naught epsilon R Q1 Q2 by R square. We get a relation between these two, that is, just divide these two equations, we'll get F air by F medium is equal to epsilon R. That is, see these equations, both the equations are similar, only difference one epsilon R is coming extra in this equation. So when we divide this with this epsilon R will come in the numerator and all other terms will cancel. This will cancel, this will cancel, cancel. So only epsilon R will remain. So we get F air by F medium is equal to epsilon R. That means F medium is equal to F air divided by epsilon R. Usually value of epsilon R I have told, epsilon R will be greater than 1. That means F medium reduces, right? Here actually it reduces compared to F air. If we initially the force of interaction when they are kept in vacuum be F air, then when medium is introduced it is reduces by a factor of 1 by epsilon R. That is F medium decreases by factor 1 by epsilon R, and the question is, but what factor F air changes? So actually F air is epsilon R into F medium. F air will be more compared to F medium, or F medium will be F air by epsilon R. So this is the answer for that question, and remember this point, okay? This is an important concept related to the permittivity and the medium. Now we'll move on to Coulomb's law in vector form. Why we have to study Coulomb's law in vector form? Because force is a vector, right? Force is a vector quantity. So it is better to write Coulomb's law in vector notation. And one more thing you might have noticed is the resemblance of Coulomb's law and universal law of gravitation. Last year you have studied universal law of gravitation. So it is similar to Coulomb's law. There we were finding the gravitational force between two bodies, two masses. Here Coulomb's force between two charges. There also relation is G into m1 m2 by d square. Here also K into q1 q2 by r square. Similar. There also we have obtained the vector form of gravitational law. So here, in order to introduce the vector notations, you should remember the notation vector, important vector notations and position vector, unit vector, all those things once again that you have studied last year. So let the position vector of charges q1 and q2 be represented by r1 and r2. We usually represent position vector using notation r1 and r2. So force on, and another important notation we are using here is F12 and F21. What do you mean by F12? F12 means force on Q1 due to Q2. That is denoted by F12. Similarly, F21, force on Q2 due to Q1. That is F21. These are the two important notation we are using here. Okay, F12 and F21. And here we are using 2 point charges numbered 1 and 2 and unit vectors r1 and r2, then f12, f21. Now we have to see the vector from 1 to 2. It is denoted by r21, where r21 is equal to r2 minus r1. So it will be clear in the next slide with respect to the diagram. And this equation we are getting from the triangular law of vector addition. Okay, two vectors, if we have, how to find the resultant of two vectors, addition, vector addition and vector subtraction we have studied. Based on that we are getting this relation. Same way, vector leading from 2 to 1 is denoted by r1 to this you just note. Okay, 1 to 2 is denoted by r21 because 1 to 2 the relation is r2 minus r1. It is denoted by r21 and 2 to 1 is denoted by r12. Okay. Now see here. So we have two vectors q1 and q2. This is the origin. Then position vector of q1 is r1. Position vector of q2 is r2. These bold letters are used to represent their vectors. But when you write in the notebook, you have to use the symbol of vector. Put an arrow mark on these r1 and r2. But in the course book, they use capital letters to represent vectors. So r1 is the position of q1, r2 is the position of q2. Now we need to find out the resultant of r1 and r2. That will give you the distance between r1 and r2. So that is given by r21, which is equal to r2 minus r1. So distance between r1 and r2, or the resultant of vectors r1 and r2 by triangular law of vector addition is given by r2 minus r1. This is r2. Since they are in opposite direction, minus sign, r2 minus r1. So this is our vector r21. R21 denote the vector or position vector, resultant of position vectors r1 and r2, which is directed from 1 to 2. Okay, r21 denote the position vector directed from 1 to 2, not from 2 to 1. Okay, 1 to 2. Now see this diagram. Two more diagrams are given. So this diagram gives when the two charges are same charges, means both are positive or both are negative. So in that case, q1, q2 greater than 0. This condition is when both the charges are positive or both the charges are negative. You just think when both the charges are positive or both the charges are negative, what type of force of interaction exists between these two charges? Repulsive, right? Repulsive force, because they are both same charges, like charges repels that you have studied. So repulsive force. So accordingly, here see the direction of forces. F12, that notation you are already seen. F12 is the force acting on 1, force acting on q1 due to q2. So F12 will be away from q2. See, repulsive. This is the direction of F12, away from q1. Similarly, F21, force acting on 2 due to 1. That will be acting in this direction, away from q2. repulsive. So this charge will try to repel from Q1. So like this. Similarly, this charge try to move away from Q2. So the force of interaction will be in this direction. And the unit vector. So another thing is position. These are position vectors. And what is unit vector? Unit vector is the vector which is used to represent the direction. Okay, direction. And it has magnitude unity. So here you can see the unit vector R21 is equal to R21 is directed R21 is directed from 1 to 2. Okay, it is clear, right? R21 is directed from 1 to 2. So this is R21 which is directed from 1 to 2. Now see second diagram, this diagram, Q1, Q2 less than 0. What does it mean? One charge is positive and another charge is negative. Like Q1 can be positive and Q2 negative, or Q1 can be negative, Q2 can be positive, unlike charges. So what will be the nature of force of interaction between these two charges? Attractive, right? Attractive. Opposite charges or unlike charges attracts each other. So accordingly, you will get the direction. So note down the direction. F12, force acting on 1 due to 2 will be towards Q2, Q1 to Q2. Similarly, F21, force acting on 2 due to Q1 will be towards Q1. See, attractive nature. But in both the cases, you can understand F12 and F21 are in opposite direction, right? F12 like this, F21 like this, opposite. F12 like this, F21 like this, opposite. And the unit vector. What is the direction of unit vector R21 from 1 to 2? R21 is the notation used for unit vector which is directed from 1 to 2. So these things you need to understand. Vector notation and vector form of Coulomb's law. So here you can see the magnitude of vectors R21. This is bold letter, no? So these two are vectors. Their magnitude is given by R21 and R12. And their magnitude will be same, only the directions are opposite. And we have used the notation to represent unit vector. So R21 is given by this formula also we have studied in the class 11. That vector notation. Unit vector is given by a vector position vector divided by its magnitude. So R21 is equal to the vector R21 divided by its magnitude. Similarly, unit vector R12 is equal to R12, the vector R12 divided by its magnitude. So their magnitude will be same, but only direction will be opposite. So this is the Coulomb's law in vector form. So Coulomb's law between 2 point charges Q1 and Q2 located at R1 and R2 position R1 and R2 is expressed as F21. What is the meaning of F21? Force acting on charge Q2 due to Q1 is given by 1 by 4 pi epsilon naught Q1 Q2 by R21 whole square into unit vector R21, where R21 is the vector directed from 1 to 2, and F21 is also acting from 1 to 2. Some important points are this equation of Coulomb's law in vector form is valid for any charges, whether it is positive, negative, one is positive or one is negative, like that. Only thing is that you should be careful about the direction. F21 is acting along R21. When both the charges are of same sign, both positive or both negative, we have seen force of interaction will be repulsive and the direction is given by unit vector R21. Second case, if both are opposite sign, then what is the direction of F21? Just opposite of R21. That is denoted by R12. Okay. The opposite of R21 denoted by R12. So accordingly, we'll get equation. So we can write equation of Coulomb's law for both the cases. Same equation you can write, only thing is that they are acting in the opposite direction. In the beginning, that diagram I have shown no F12 and F21 are acting in the opposite direction. That means F12 is equal to minus of F21. So, okay, this is an important result. This is the Coulomb's law in vector form. So remember, F12 is equal to 1 by 4 pi epsilon naught Q1 Q2 by, if here 1 2 is coming, here also 1 2, here also 1 2. and it is equal to just the opposite of F21. Along with this, we have a definition for 1 Coulomb, that is from the equation of Coulomb's law. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So in that particular equation, if you substitute the charges are unit charges Q1 and Q2 as 1 Coulomb and the distance is 1 meter, the equation reduces F is equal to 1 by 4 pi epsilon naught alone, and that value of that constant is given by 9 into 10 raised to 9 Newton. So from that we are defining 1 Coulomb. So definition is 1 Coulomb is defined as that charge which when kept 1 meter apart from an equivalent similar charge in vacuum repels with a force 9 into 10 raised to 9 Newton. This is the just definition you need to remember. Certain significance of Coulomb's law. These are certain significance. Just go through the significance. What are the significance? Force. It is the Coulomb's law is the force that binds electrons together to the nucleus of the atom, and it binds atoms together to form molecules. It binds molecules to form solid or liquid. It reveals that electric interaction can be attractive or repulsive. It reveals that electric force is central and obeys inverse square law. So these are certain significance. Along with this, I ask you to read the course book till this topic. Okay, read it clearly, understand it properly, make a notes of this, and if you have any doubts, please ask me. Okay, thank you.